Hello, everyone. Today we are going to present to you about soil analysis. And in this experiment, we are going to determine the macronutrients as well as the micronutrients of phosphorus, potassium, iron, as well as copper. So in this presentation, there will be three things that we are going to discuss. The first thing is about introduction. So in this introduction, we are going to explain briefly about soil analysis. And then the second, we are going to discuss about the procedures of the soil analysis from each of macro and micronutrients. And the third one was the result of the experiments. Okay, so let's jump into the first thing that we're going to discuss about the introduction about soil analysis. So, what is soil analysis? Soil analysis is determination of the level of nutrition found in a soil sample in a set of various chemical processes. So as we know, soil contains a lot of nutrition. So soil analysis is as analyzing or getting the information of what does the soil contains. So why do we do this soil analysis? There are a lot of reasons why do we do this, and here we provide three reasons why. The first one was to provide an accurate assessment of the soil's fertility. So by doing this soil analysis, we can actually know what does the soil contains. Therefore, we can adjust its fertility, or we can know whether the soil is fertile or not. Therefore, we can know whether do we need to add fertilizers or not, whether it is suitable for us to plant in that soil or not. And then the second one was to protect the environment from contamination by runoff and leaching of excess fertilizers. So excess fertilizers can end up with the soil being contaminated and destroying the environment. Therefore, to prevent that from happening, we need to analyze the soil. Therefore, we know whether the soil needs fertilizers or not. And then the third one was to improve the nutritional balance of the media and to save money as well as to conserve energy. Again, by doing this soil analysis, we can know what the soil contains. Therefore, we can also know what kind of fertilizers that the soil needs to be fertile and to have a balance in nutrition. Therefore, we can actually save money from actually adding some fertilizers that the soil doesn't need and to conserve the energy. And then the third one is to how do we do this soil analysis? Basically, since soil contains a lot of nutrition, a set of treatments was done to analyze different nutrition. So in this case, we are going to analyze phosphorus, potassium, iron, as well as copper. For each one of the nutrition, a set of treatments was done differently. So here are the procedures or a set of treatments that were done to the soil to analyze each and every one of the nutrition.
The first parameter that I will be explaining is phosphorus, and in order to determine its concentration of phosphorus in the soil, I use Aes Method. The sample soil was located in Shaanxi, China, which I use for this discussion, and the soil sample were first collected from various areas, and then it was crushed, sieved, and air dried for about 2 to 3 days, and then 1 gram of air dried soil and a 20 ml of sodium bicarbonate 0.5 molar was mixed for about 30 minutes, and then the sample was then added with molybdate ascorbic acid reagent, and the solution will appear as a blue color, and then the solution will then measure its absorbance by using UV-vis spectrophotometer with the wavelength of 880 nanometer. And then the absorbance values were obtained and the phosphorus content can be calculated. After adding the molybdate reagent, the temperature was adjusted into various temperature and 1 centimeter light diameter was applied for 30 minutes.
To determine the potassium content in the soil, we used ammonium acetate. Firstly, the soil was air dried and passed through a 2mm sieve, and then the soil was transferred into a 100 milliliters polyethylene bottle along with 50 milliliters of ammonium acetate in acetic acid. The mixture was shaken for 30 minutes in a shaker. Then the solution was allowed to stand for several minutes. After it was precipitated, it was filtered using a filter paper. And then a calibration curve was made by measuring the absorbance of various concentration of potassium standard solution. And this was done using a flame photometer. And then the absorbance of the sample solution was also measured using flame photometer. And then the concentration of the sample was determined by the equation that was obtained from the calibration curve.
Next parameter is ion. Atomic absorption spectroscopy was used to determine the concentration of ion in the soil. Firstly, soil sample was collected from 6 different locations, and then 5 subsamples were randomly collected at a depth of 0 to 30 centimeter to make a composite sample at each sampling store. And then each soil sample was placed inside a polyethylene bag, and then it was taken to the laboratories, and then it was spread and air dried. And then after it was dried, it was then sieved through 2mm sieve, and then as much as 1 gram of each soil sample, it was placed inside the flask, and the sample was mixed with a mixture of concentrated HNO, HClO4, and HF in the ratio of 3 to 1 to 3. Afterwards, the mixture was heated to 80 degrees Celsius for about 3 hours. The product was then filtered into 100 ml standard plastic bottle and made into 100 ml with deionized water. Lastly, the solution obtained was then measured using atomic absorption spectroscopy.
To determine the copper content in the soil, there were 2 types of method that was conducted, which is it was analyzed using energy dispersive X-ray fluorescence, or EDXRF, as well as atomic absorption spectrometry, or AAS. So all of the sample was prepared first, which is the sample was air dried and sieved, and it was treated by nitric acid, and the sample was incubated for 15 days to maximize the acidification reaction. For EDXRF, 200 milligrams of the sample were taken to make pellets, and the elemental profile of the soil was obtained using the EDXRF spectrometer. For AAS, 500 milligrams of the fine soil was placed in a digestion vessel along with nitric acid, hydrogen fluoride, and perchloric acid. The vessel was then covered and placed in a boiling water for 2.5 hours. The contents were fumed at 200 degrees Celsius. The residue that was contained was diluted in 2 milliliters of nitric acid and perchloric acid, and it was fumed again. The residue was then dissolved in nitric acid and diluted in 100 milliliters of high purity water. The total copper concentration was determined using AAS, and a calibration curve was also made by measuring the absorbance of copper standard solution using AAS as well.
Next is the results and discussion of this research. And here's the result for phosphorus. Why phosphorus is important to be determined its concentration. It is because phosphorus is a major essential plant micronutrient which is needed for plant growth and development. And however, extensive cultivation of vegetables and other crops along with natural hazards cause depletion of natural phosphate content in the soil. Therefore, phosphate fertilizers have been used to overcome this depletion and enrich the respective soil. And the choice of method used for phosphorus determination depends on the soil condition in the area. So it is not only Aes method that can be used, but there are also various methods that can be used to determine the concentration of phosphorus, such as calorimetric method, Murphy and Riley method, and others. Besides of the condition of the soil, Aes method was chosen because it is a low-cost method and it is widely used for mild acidic to basic soils. And sodium bicarbonate has been widely used for soil phosphorus because bicarbonate ion can remove calcium from the system, which solubilizing the calcium phosphate. And then it is measured by index of availability of phosphorus. Molybdate ascorbic acid reagents react in acidic solution with orthophosphate to form a heteropoly acid, which can be reduced by ascorbic acid to form an intense blue color. And then the absorbance was measured at 880 nanometer. 880 nanometer was chosen because the solution that is analyzed is a colored solution, so it is perfect to use a high wavelength. The color temperature was controlled by an indicator, and the available phosphorus in the soil was measured at 5 different temperature levels, such as 10 degrees Celsius, 15 degrees Celsius, 20 degrees Celsius, 25 degrees Celsius, and 30 degrees Celsius. As you can see in the table below, the color temperature increases as the availability of phosphorus content of all the samples increases. At 25 degrees Celsius, the availability of phosphorus content was 2.7 to 26.4 mg per kg, with an average value of 8.5 mg per kg. 25 degrees Celsius is used as a standard temperature. At 10 degrees Celsius extraction, the content of phosphorus decreased by 0.9 to 4.9 mg per kg. For temperature 15 degrees Celsius, the phosphorus content decreased by 0.7 to 3.4 mg per kg. And for the temperature 20 degrees Celsius, it's decreased by 0.5 to 2.1 mg per kg. And for the temperature 30 degrees Celsius, it's increased by 0 to 0.4 mg per kg. These values were compared with the standard temperature, which is 25 degrees Celsius. And as the difference between the available phosphorus content and the temperature at 25 degrees decreased, the difference between the effective phosphorus content between the temperatures also decreased. The difference of phosphorus content is due to the effect of extraction temperature on soil available phosphorus. It shows that the phosphorus content increased significantly at the color temperature between 20 to 25 degrees Celsius and increased slowly at 10 degrees Celsius to 20 degrees Celsius and 25 degrees Celsius to 30 degrees Celsius. The availability of phosphorus content between 25 degrees Celsius and 30 degrees Celsius did not have a significant changes, and it is still in the error range allowance. However, for the temperature of 10 degrees Celsius, 15 degrees Celsius, and 20 degrees Celsius, there were significant differences which were beyond the error range allowance. This phenomenon might be due to the temperatures not reaching full color. Therefore, the phosphorus content cannot be detected effectively. And for the experiment, the most appropriate color temperature should be controlled at 25 degrees Celsius to 30 degrees Celsius for the determination of soil availability of phosphorus. After the absorbance values were obtained, the calibration curve can be drawn and determines its equation, and then the equation can be used to calculate the availability of phosphorus content. And then here we got 16.85 ppm, which from the table below, it shows that the available phosphorus is medium related to this phosphorus content of soil.
Okay, so now we're getting into the result of potassium analysis. So basically, potassium is the major nutrient and also most abundant element in soils. But potassium content in soil varies from place to place based on the physiochemical properties of the soil. And potassium exists in various forms. For example, it can exist in minerals, non-exchangeable ions, exchangeable ions, and solution. So in this particular case, we are going to measure or analyze the content of exchangeable potassium in the soil sample. So ammonium acetate was used to analyze the potassium content in the soil. Ammonium acetate that is buffered at pH 7 was used, and then the sample was air dried to in order for the sample to be stored for a long time, and it was sieved through a 2 millimeter sieve to obtain a uniform size of the sample, as well as to remove any unwanted particles. And then a calibration curve was made to obtain the linear equation to calculate the potassium content later on, and it was made by measuring the absorbance of various concentration of potassium standard solution, and this was done using a flame photometer. From the literature that we get, it uses 4 different methods to determine the exchangeable potassium content in the soil. But in this particular case, we will just focus on the usage of ammonium acetate to determine the exchangeable potassium content. And as we can see from the table, there are 7 types of soils that was determined, and as well as the result of the exchangeable potassium content using ammonium acetate. So from the table in the previous slide, we can see that the content of potassium or exchangeable potassium in the soil that was analyzed values in the range from 0.28 to 1.1 MEq per 100 grams of soil, or we can say it's about 107.7 to 426.9 ppm or parts per million. The potassium content from all of the sample were considered as moderate, while in the seventh soil, it is substantially higher than the others, which has the highest potassium content, which was 426.9 parts per million. And it is considered as still normal from the literature, which is the content of exchangeable potassium in soil should be 40 to 600 parts per million, but it is considered high from the table below that is attached, which is the potassium content considered as high, very high, in fact, when it is ranged from 401 to 600 compared to the other soils.
Iron is involved when a plant produces chlorophyll, which gives the plant oxygen and healthy green color. Soil that contains excesses of alkaline, which often causes an iron deficiency in the plants in the area. Thus, to improve the quality of the soil, iron fertilizers can be added. Soil samples were first collected from 6 different locations from various areas to allow fertilizers and lime application to vegetate the soil from each area separately. The samples needed to be air dried and sieved in order to help determine the moisture content at different tensions. It equally increases the ease of handling of the soil samples during analysis and the concentration of solutes in the soil solutions, which may lead to increased sorption on soil surfaces. The sample was added with minerals acid, heated and filtered. It was then analyzed using AAS to determine the concentration of heavy metals. In the literature, it is stated that interference from citric acid has been reported to suppress the absorbance by up to 50% for a citric acid level of 200 microgram per milliliter. The interference has been minimized by measuring the absorbance in the presence of phosphoric acid, select the optimum burner height, as well as the use of nitrous oxide acetylene flame. From this table, the calibration curves for all the methods showed good linearity with coefficients of determination ranging between 0.9997 and 0.9999, which were greater than the expectable limits. This performed a good correlation between concentration and absorbance, indicating good calibration of the instrument. Iron element has IDL of 0.005 milligrams per liter, LOD of 0.203 milligram per kilogram, and LOQ of 0.771 milligram per kilogram. Copper is important to be determined in the soil because copper is one of the 8 essential plant micronutrients. It is required for various enzymatic activities in plants and for chlorophyll and seed production. Excessive amounts of copper in the soil can lead to diseases like ergot, which can cause significant yield loss and small grains. The soil sample were first collected in areas with various fertilizers treatment to estimate the parameters of the total population. As much as 24 samples were collected for the analysis, and large number of samples were advised so that the sample desired can be obtained for subsampling. To obtain a representative sample, and analysis of the sample gives average values for the entire area. The samples were air dried to provide the dissolved organic matter and sieved due to remove the unwanted, mainly roots and some particles. HNO3 was added to the sample to remove H plus excess and adjust the pH of the sample about 5. In this experiment, the copper in the sample were being analyzed using 2 methods. Firstly, the sample was analyzed using EDXRF. It is a non-destructive, rapid, and highly accurate and environmentally friendly analysis. The principle is direct excitation, a process by which atoms in the specimen are excited by primary photons from external sources, such as X-ray tube, radioactive sources, and synchrotron beam, to produce primary fluorescence. EDXRF can detect a wide range of elements simultaneously in a highly accurate and fast process. For Aes method, there are 2 types of methods were conducted. The first method is to use open vessel. HNO3, HF, and HCl04 were used for dissolution and appropriate combination of acids which successfully can decompose various geological samples. HF is almost always mixed with other oxidizing acids such as HNO3, HCl04 to ensure complete dissolution and to produce uniformly high oxidation states in the final solutions. These samples was then boiled to kill the bacteria and stimulate the pores of soils. The second method is to use closed vessels by heating the sample using microwave and mixed it with HNO3, HF, and the ionized water. Microwaves can rapidly help dry the sample evenly. In addition, the moisture content of the sample can also be measured. The vessel has to be tightly sealed with a plastic wrench to prevent air contamination, and the sample was cooled, diluted, and filtered through a filter paper. Then, from both preparation methods, the concentrations of the sample was analyzed using AAS. It shows from this table that most of the 4 heavy metals were obtained maximum when the samples were prepared by open vessels dissolution method. From the mean values obtained such as 8.16, 14.82, and 14.16, the EDXRF and AAS have dissimilar results. When the concentrations of elements have high concentration values in the samples, the results of both techniques were comparable. This shows that the concentrations of element was close to detection limit is less accurate. However, it was found that for low concentrations of copper levels, the results of AAS were more near to certified value than EDXRF, and it is further investigated using linear regression. From this research, it is concluded that phosphorus is a major essential plant micronutrient which is needed for plant growth and development. At room temperature, the phosphorus content was 2.7 to 26.4 milligrams per kilogram. As the temperature decreases, the content of phosphorus also decreases. The available phosphorus content was at 16.85 ppm. Secondly, potassium is the major nutrient and also most abundant element in soils, but the potassium content of the soil varies from place to place based on physicochemical properties of the soil. The potassium content from all of the samples is considered as moderate. Third, iron is involved when a plant produces chlorophyll, which gives the plant oxygen and healthy green color. The calibration curves for all the metals showed good linearity with coefficients of determination ranging between 0.9997 and 0.9999. This performed a good correlation between concentration and absorbance, indicating good calibration curves of the instrument. Iron has IDL, LOD, and LOQ number of 0.005 mg per liter, 0.203 mg per kilogram, and 0.771 mg per kilogram, respectively. Lastly, copper is important to be determined in the soil as it is one of the 8 essential plant micronutrients. It is required for various enzymatic activities in plants and for chlorophyll and seed production. From the mean values obtained, such as 8.16, 14.82, and 14.16, the EDXRF and AAS have dissimilar results. However, it was found that for low concentration of copper values, the results of AAS were more near to certified value than EDXRF results. Thank you very much for your kind attention. Assalamualaikum warahmatullahi wabarakatuh.